All right, today we're going to go over your heat and temperature notes. Do this all in one shot, and just going to go over our basic intro. So, with heat and temperature, well, what exactly is heat and temperature? Well, first up, the first one we'll talk about is temperature. That is how hot or cold something is compared to a standard, some kind of value that we can compare to. Because if you just ask someone, is it hot, is it cold? Everyone kind of has their own preference, but if we compare it to a known value, then we can know exactly what temperature we have. Like if the air temperature happens to be 7 degrees Fahrenheit, I know how warm that is. As to, I just say, oh, it's pretty warm outside today. Then I might not necessarily know exactly what it is. Now, what exactly is temperature? It is proportional to the kinetic energy average of atoms and molecules. And all matter, no matter um, what type of form it is in. If it is a element, if it is a compound, if we look at everything on the atomic scale, there is always going to be some motion, some wiggling. And if we happen to take a look here with water, right now we happen to have it in a solid state. But if you notice on the screen, there happens to be a bunch of just little wiggling. The molecules are kind of bouncing around. They're kind of slipping past, but they're generally holding about roughly the same spot. I add a little bit of heat to it. I give it a little bit more energy. Notice that the molecules are wiggling around just a little bit more. I give it some more energy. Now all of a sudden, now it's no longer holding those gaps. And what we're actually seeing right now is liquid water. Um, where there's not much gaps, there's not really much space, where there's big air gaps in between. And occasionally you might notice one of these little molecules that get kicked up out of there. If this was open, what we would be seeing right there, that's a process called evaporation. If I get a little bit more heat, there's even more molecules, more. Here, if I stop about 80, we're not quite at boiling, so we're not getting into any gaseous particles. But notice there's a lot that are really spinning really quickly. They're moving around. And if I would take a look at all that kinetic energy, all that energy of motion, what I'd end up looking at is I have what I define as temperature. And whenever there is more in a gas, they're more spread out, they're bumping around, they just have a lot more energy than whenever they have a liquid, or maybe whenever they're even in a solid, where we even get some of these water molecules locking in and we end up having these big air gaps. And that's why ice actually floats in water. It's because it has more space in between the molecules. There's three different scales that we can measure in. There is Fahrenheit, which we measure in the US. Pretty much anytime you watch the weather, you're going to notice what the degrees are in Fahrenheit. In science, we happen to use Celsius as kind of more of our standard. What that does is with water, it takes two known values for water at 0 degrees Celsius. That's whenever water goes between the solid and liquid phase. And whenever it goes to 200 or 100 degrees 100 degrees Celsius, it ends up being where water goes between the gas and liquid state of matter. For Fahrenheit, that value is at 32 and 212 degrees. And then a little bit later on, after the Celsius scale was well, pretty much discovered, Lord Kelvin, he went through with temperature. He didn't really kind of like negative numbers. So what he ended up looking at was if you were to take all the energy away from a system to where there is no actual motion in any of those molecules, that's the point where all motion stops. And it cannot actually have a colder temperature than what's called absolute zero. And that value is at 0 Kelvin, or negative 273 degrees Celsius, because that's really just a conversion between them. And it doesn't matter if I have water, if I have neon, argon, oxygen, all motion, all little wiggles. There is no motion at absolute zero, and that is at 0 Kelvin. And going down, going down, going down. Almost there. And there's 0 Kelvin. And as you notice on the screen, there's not even a just slight wiggle. Everything is there that is stopped. Now, how do we go between the two, or between the scales? Celsius and Kelvin, all it is just adding or subtracting 273. If I want to go from Celsius to Kelvin, I want to go from the one that has Kelvin by itself. So I'd plug in Celsius, I'd add 273. If I'm going from Kelvin to Celsius, I just subtract 273. Again, if you're wondering if you did this right, if you end up with a negative Kelvin, you did something wrong, because you cannot have a negative Kelvin. Over here, going between these ones, a little bit more math involved. I always remembered the going from Celsius to Fahrenheit off the top of my head. You take 9 divided by 5 and multiply by your temperature in Celsius, and then just add 32 degrees to it. Over here, if I want to take the Fahrenheit and go to Celsius, I have to plug in, and I need to do what's inside the parentheses first, then multiply by 5 and divide by 9. That's how I would enter the fraction. So if I have 55 degrees Fahrenheit, I want to know what that is in Celsius. I take 55, I subtract 32, that gives me 23. 23, I multiply by 5, I divide by 9. Because that's all a fraction is you're multiplying the top number and dividing the bottom, and that is at 12.8 degrees Celsius. If I'm using the other one, let's just say I had 10 Celsius. I'm going to multiply by 9, divide by 5, and then add 32. 10 degrees Celsius is 50 degrees Fahrenheit. Okay. Now, most matter will undergo this property. It's called thermal expansion. Whenever things warm up, the matter will expand because it has more energy. Those molecules that I showed you a little bit ago, they're wiggling more, they're bouncing around more, they have more energy. And as things have more energy, they kind of spread out naturally. Imagine just giving a group of kindergartners a whole bunch of pixie sticks and tell them to sit around in a nice little circle and be quiet and listen to a story. Well, as they keep getting more energy, they're going to want to probably start poking the people next to them, not sitting still, not listening, and next thing you know, you have a little bit of a crazy day, and all because you gave them more energy and that sugar. Well, same thing with the heat. You give them more energy, those molecules bounce around a lot more. Now, where might you notice some things that deal with thermal expansion? On bridges, they have what's called expansion joints. So like if you notice this picture right here, this shows an expansion joint on a bridge. This allows for the matter to expand and contrast so that the bridge doesn't buckle and doesn't break. Or maybe if you notice this on the side of a building, this allows the building to expand and contrast as it heats and cools. On the rails, on railroad tracks, where you have these, which allow the rails to expand or contract based upon their temperatures. It's why basketballs, if you leave them outside in your car and bring them inside during the winter, why they will seem like they're flat. Why your car tires, if it gets a real cold morning, you might go out, you might notice the check engine or check air tire pressure light comes on. But don't put a lot of air in them, because as soon as things warm up, those molecules will start bouncing around more, and you could end up blowing out your tires. Bimetallic strips are used in older homes and old thermostats. If you ever had to take one off, bimetallic strip thermostat image. Didn't need to put that eat there. Basically just looks like a little coil. Where's a good one? Okay, right here. This little circle part, this is the bimetallic strip, and one part of it will expand a little bit more than another one and kind of bend around. And I actually have a little demonstrator here. So this I typically show in class. I have these, but and that was perfectly straight when before she started heating it, and one side expands more than another, so it starts to bend up where the other side doesn't bend as much. Okay. Thermal equilibrium occurs when any two or more objects are in contact with each other. Will have, if they are touching, then eventually they will have the same temperature and reach what's called thermal equilibrium. This just happens to be for temperature conversions. Just remember, Celsius is your middleman. If you're going from Kelvin to Fahrenheit, you have to do 2 steps. If you're going from Fahrenheit to Kelvin, 2 steps. But if you're Celsius, either way you go, it's just one. Okay, what is heat? Heat is energy that always moves from a higher temperature to a lower temperature. Things always go from high to low. Um, if I have a ball, it's not going to just roll up a hill on its own. It's going to go from that high area, that high potential, to an area of low potential. And that's the same thing because that's what heat is. Heat is energy, and it's energy movement. It's energy that moves from one object to another due to a temperature difference, and it's always going to go from a hot object to a cold object. The units are what we measure in, still for energy, it's still measured in joules. And we actually have two equations for heat. Heat is variable Q, that's over here on the left. It's at, and we can calculate it by one of the two equations. If we're using for a temperature change, that's the one over here on the left, where we have mass multiplied by the specific heat capacity of the substance and the change in temperature. Over here we have, this is the mass, and this is what we call latent heat. That is the heat needed for a phase change, so going from a different state of matter to another. And heat energy always goes from hot to cold. Now, how can heat get transferred? Well, there's three different methods that allow for heat to go from one object to another. The first one that we'll talk about is what's called conduction. Conduction occurs whenever any two objects are in contact with each other. Um, Basically, you put a pan on a stove, the pan eventually gets hot. That's conduction. I had my coffee pot. It was warm. I put it on the counter for a minute. I put it back under the coffee maker. I felt the counter, and the counter was hot. Well, it was hot because it was touching the coffee pot. Next is what's called convection. Convection occurs by currents that transfer energy. Now, again, this is usually something I typically will show. Here, this is what's called a convection tube. This just has water. One side of this gets heated, and he's going to put in a little piece or a little drop of food coloring. And what you're going to notice is where you have the water getting warmed up, warm stuff rises, cold stuff sinks. Maybe you notice in the summertime if you jump in a swimming pool or a lake, how the top of the water is real warm, but if you dive down maybe 6, 8 feet, the water gets really cold. That's because warm rises to the top, the cold stuff will sink. Think back to the water cycle. Water gets evaporated at the surface, it goes up into the air, it cools down, forms clouds, and eventually comes back down in the form of rain. So here he's going to put the drop of food coloring in. All that food coloring is going to do is so we can see the water, which way it actually moves. So again, this is heating up down here. Notice we're starting to get the water to start moving. And here it's moving back up over here again. Yep. Another method where we can actually take a look at the convection currents is what's called a little chimney apparatus. So if you ever happen to have a home with more than one fireplace, it's not good to have both of them open because you can actually end up making your house colder. So you light one candle on one side, this front is closed. This will start heating the air up, and this heat is going to rise. Well, as this rises, it creates a vacuum, and it's going to suck cold air down from over here. It'll start getting going up there. Okay, and the third method is what's called radiation. This radiates over empty space. It's kind of like how, like in the form of waves and light. It's why you end up seeing, like, why the sun feels so warm, even though it's traveling through empty space and getting here to Earth. Why you can be sitting around a campfire, not necessarily be touching it, but you can just feel that heat coming at you. That's radiation. And what's defined as internal energy is the total amount of all energy, the kinetic, the potential, the rotational inside of a substance. Okay. Now, why do objects that end up having the same temperature feel like they're at different temperatures? So, at this point in class, I would tell the kids, "Hey, touch the red part of your seat and then touch the metal. Does one feel like it has a different temperature than another?" And they will say that it does. And the reason for that, even though that they're in the same room that has been the same temperature all day, where the reason for it is because one of those materials is a conductor and one of those is an insulator. A conductor will transfer heat very quickly. So, like metals, ceramics, whenever you touch them, that heat goes to your hand very, very quick. But when you touch an insulator, that allows heat to transfer very slowly. So, wood, air, rubber, clothing, water, those are all insulators. It takes a really long time for them to heat up and takes a really long time for them to cool back down. Um, the Also would probably go through and show you guys a video on fire walking where you can actually walk over coals, but coals are just, it's wood. It's a better insulator. So it doesn't allow the heat from the wood go into your foot as long as you're quick about it. I watched friends of mine, they'll juggle hot coals whenever we're sitting around a campfire. They're not holding on to them, but if they just kind of touch them for a brief period, it doesn't burn their hand. But if you would do that same trick and try it with, say, a little piece of metal, that metal is going to instantly scar your flesh because that heat and energy is going to go right into it. Um, Different applications of conductors and insulators. Walking down the hallway to your bathroom, you go from carpet to tile. How it feels like there's a big difference, but it's in your house. It's the same temperature, but just the heat's going to leave your foot faster than what it is whenever you're on the tile than it is whenever you're on the carpet. Pizza ovens are designed so that they are allow for heat to transfer quickly into the crust. If you go to a store for some frozen yogurt, why that ends up getting feeling like a little bit colder than ice cream is because yogurt is a better conductor than ice cream. Clothing, having more layers on creates different air pockets, which ends up allowing for more insulation. Magic acts like walking across a burning bed of coals. Again, differences in materials. If you happen to be going across metal, that would instantly just destroy your feet. But walking over the coals as they cool off, it allows it to be fine. In the wintertime, don't ever be like the kid in A Christmas Story. Put your tongue on cold metal. The heat leaves your tongue very, very quickly. And next thing you know, you end up having a phase change and your tongue is stuck on the metal. Insulation in your homes, how that ends up creating a barrier from the inside to outside and not allowing the heat to transfer and escape your homes. Now, what exactly is the first thing that we'll look at for heat? What will it depend on? The amount of heat it will take to change a temperature substance depends on three things. What is the size of the object? You know, if I want to heat up a small pot of water versus a big pot of water, that makes a difference in how long I have to heat it. What substance I'm heating up? If I have water in the pot versus just the pot itself, the pot's going to heat up a lot faster than what the water is, just because it's a different type of material. And the third thing, how much energy I need, is how big of a temperature change do I want to make? Do I want to make a small temperature change, or do I want to make a large temperature change? So our equation for heat, that is letter Q, measured in joules, is MC delta T. And what this delta symbol means, it means change in temperature, where you're going to measure the final temperature minus the initial temperature. And we want to make sure we measure that in degrees Celsius. Specific heat capacity we're going to talk about here in a minute, but it is measured in joules per kilogram degree Celsius. And those are just values that happen to be either in a chart or what we will end up being solving for. Okay. That variable C, that is one that is new. That stands for the specific heat capacity, and that is the amount of energy needed to change the temperature of 1 kilogram of substance by 1 degree Celsius. Now, the higher the specific heat capacity, the more energy is needed, and the harder it is to change the object's temperature. The lower the specific heat capacity, the easier it is to change the object's temperature. So, water has a really, really, really high specific heat capacity, like 4,186 joules per kilogram degree Celsius. Lead, if I had a chunk of lead, it only needs 129 joules per degree Celsius. So if I would actually compare those two values, divide by 129, it takes 32 times more heat to change the temperature of water than it does lead. One of the things that I notice that I do at times when I'm baking something in the oven, I'll have it covered in foil. I'll open the oven door, I'll let the heat come out for a minute, but then I'll actually go in and I'll touch that aluminum with my hand, but I'm not going to touch it with glass, and I'm not going to put my finger in the water that might be there, because that's going to burn. But I can touch that aluminum foil pretty quick, and it's not going to hurt my hand. The higher the specific heat capacity, the harder it is to change the temperature of the substance. It's more like thermal inertia. Now, that has some different applications and examples. Think about the food on your plate, how things will warm or cool differently. I'm someone who likes breakfast, and I'll eat brunch or dinner sometimes. I like fried potatoes and eggs. Well, it takes a lot longer to cook the fried potatoes than what it does the eggs. Hence, whenever it's on my plate, I always end up eating my eggs first because they cool down quicker. They have a much smaller specific heat capacity than the potatoes do. Potatoes take a really long time to heat up, and they take a really long time to cool back down. Water's high specific heat capacity has an important impact on weather and organisms that live in there. You don't want something to heat up too quickly. Like all the fish would end up getting boiled alive if they had all that heat from the sun. Also, if you ever notice, if you're generally around a body of water, typically the climate's a little bit more mild. You get a little bit more breeze coming in from the ocean during the day. Then it goes back out towards the water at night because of the difference in heating. And if you put 100 degree piece of lead and 20 degrees of water and allow it to reach equilibrium so they have the same temp, it's going to be a lot closer to 20 degrees than it would 100. I think that finishes up our notes.